Okay, get ready, because today we are taking on a topic that is infamous for, well, kind of turning brains to mush. It's the three-body problem. You want to really get this, and trust me, once you do, you'll be blowing minds left and right.
Right.
So basically what we're talking about here is trying to figure out how three objects will move when they're all pulling on each other with gravity.
Yeah.
Seems pretty straightforward, doesn't it? Like, just a game of cosmic billiards.
Well, if you remember those physics problems in school where you had planets making those perfect little ovals around stars,
Yeah.
you're actually seeing the beauty of the two-body problem. And thanks to Newton, we've got that one pretty much nailed down.
Two-body, we're golden. Three-body, chaos. Why does adding one more object make everything go haywire?
Think about it like this. With two bodies, like the Earth and the Moon, they're both kind of doing this dance around their shared center of gravity.
Okay.
It's not just the Moon going around a still Earth. The Earth has its own little wobble, too.
Ah, so it's more like a dance than one just spinning the other around.
Exactly. And that balance point, that shared center of gravity, that's the key to why we can predict their movements.
Mm.
But then toss in a third thing with any real mass, like a cosmic puppy darting between their feet, and that whole balance gets totally messed up.
So the dance floor becomes total mayhem.
Yeah, pretty much. Each object's gravity is yanking on the other two all the time, and you end up with this knot of forces that's insanely hard to untangle with just math. And it gets even wilder. There's something called the butterfly effect, where even the smallest change in how a three-body system starts can lead to wildly different results later on.
Hold on. So you're saying, like, a butterfly flaps its wings in Brazil and it could make a black hole on the other side of the universe.
Well, maybe not a black hole, but yeah. It's that sensitive to the starting point, and that's what makes the three-body problem so darn tough to solve. It's chaos theory on a cosmic scale.
I can see how this would have driven scientists nuts back in the day. Didn't Newton himself have a crisis over all this?
Oh, he did. Imagine. This is the guy who practically invented our understanding of gravity, whose laws describe the two-body problem so beautifully, and suddenly he hits this wall.
Makes me feel a little better that even Newton was stumped by this. So what did he do? Give up.
Not exactly. The
Mm.
story goes that he thought God must be stepping in every now and then to, nudge the planets back on track and keep the solar system from going kaput. Imagine a universe where God's out there playing cosmic billiards to keep everything from crashing together.
That's wild. So how do we get from needing God to fix things to actually kind of getting this whole cosmic chaos thing? Someone must have figured it out, right?
Yeah, you're right. Someone did come along and make a huge breakthrough, this brilliant guy, Pierre Laplace. But he didn't have some divine inspiration or anything. He brought a whole new set of tools, advanced math.
Okay, so was Laplace some kind of math genius who could just stare into equations and suddenly see all the secrets of the universe?
He was definitely on another level. He developed this thing called perturbation theory, which I know sounds intimidating, but it's really elegant when you get down to it. See, with the usual mechanics, we could totally predict two bodies in motion, but that third one just wrecked everything. Perturbation theory was like, hold on, we can account for those little gravitational nudges from other objects.
So instead of just pretending that third object doesn't exist, perturbation theory lets you factor it in, even if it's not the main force messing things up.
Exactly. And here's the really cool part. What Laplace realized is that over time, these little gravitational tugs from that third object, they don't always just make everything go crazy. They can actually balance each other out. So they end up making the whole system more stable in the long run.
Wait, are you serious? So you're saying that a little pull here and a little tug there can actually keep everything in check? It's like the universe has its own built-in stabilizer or something.
Kind of. It's like this huge cosmic balancing act. One object might pull a planet a bit off course for a little while, but then later on, another object's pull will nudge it back to where it should be. Laplace's work was a total game changer because it showed that even with all these crazy interactions, there could still be some order underneath all the apparent chaos.
Wow. No wonder Laplace is such a legend in astronomy and math. But if he figured out this whole three-body problem, why are we still talking about it?
Well, Laplace's work was a big deal, but he was working with a specific situation. We call it the restricted three-body problem. Imagine something like a planet going around two stars.
Oh, right, like Tatooine in Star Wars, with those two suns setting.
Exactly. In that case, the planet is way, way smaller than the two stars, so its own gravity is basically nothing. Like trying to push a boulder with a feather, it's just going along for the ride while those two stars do their gravitational dance.
So Laplace gave us the tools to understand those special restricted cases, but what about all the situations where you've got three objects, all about the same size, all yanking on each other?
Well, that's when the true chaos of the three-body problem comes out to play. And it's something that, honestly, even now, with all our fancy computers and math models, we're still trying to wrap our heads around. Because you see, the universe, well, it doesn't always follow the rules of our nice, neat models.
So wait, are you saying like most of the universe is just this big chaotic mess that we can't really even understand?
In a way, yeah. It's kind of humbling, isn't it? We've come so far figuring out gravity and how things move in space, but the three-body problem, it's a reminder that there are still huge parts of the universe where simple answers, they just don't cut it.
You know, a part of me actually thinks that is really cool. It means there's still so much more to learn. But if we can't predict exactly what this chaotic stuff is going to do, I mean, what can we even do? Just kind of throw our hands up and say, chaos wins.
Not at all. Just because something's chaotic doesn't mean we don't know anything about it. Instead of looking for those perfect, predictable solutions, we've come up with some really powerful statistical tools. It's kind of like,
Right.
think about weather forecasting.
Okay, I see where you're going with this.
Right. We can't predict where every single raindrop will land, but we can give a pretty good idea of whether you'll need an umbrella next week, right?
Right.
Same idea here. We may not be able to track the exact dance of every star in a chaotic cluster, but we can use these models to see how the whole cluster might change over time, what kinds of interactions are likely to happen, and maybe even what will happen to the whole system way, way in the future.
So even in all that chaos, we can still find patterns and make predictions, just not with the same kind of certainty we have for simpler things.
Exactly, and that's part of what makes this whole field so fascinating.
Yeah.
We're always trying to find that balance between understanding the underlying order of the universe, but also accepting that some things are just inherently unpredictable.
This has been an amazing journey. We've gone from Newton thinking God's out there moving planets around to Laplace and his mind-blowing math, and now we're talking about modeling chaos itself.
And the best part, we're just getting started. Every new discovery, every new model we build, it just gets us closer to understanding this incredible, complex universe we live in.
That is so true. And on that note, we'll leave you with one last thing to think about. If even something like our solar system, which seems pretty stable, if even that could become chaotic over really long periods of time, what does that mean for the ultimate fate of, well, everything? That's a question that still keeps astronomers and physicists up at night. And that's it for a deep dive into the three-body problem. Thanks for joining us. Until next time, keep looking up and never stop asking questions.